Hello dear students, welcome back to our YouTube channel. As you know that we are studying about integral transform. We have studied before two chapters such as beta and gamma function, in which we have studied about the definition, some basic properties and many theorems and examples based on beta and gamma function. After that we have learned about the Laplace transform, in which we have studied the definition of Laplace transform. Then we have seen the Laplace transform of from some basic functions such as 1, t raised to n, e raised to at, sin at, cos at, hyperbolic sine and hyperbolic cos. We have already seen all these basic functions. After that we have learned the property about the beta and gamma function, in which we have learned about the linearity property, then shifting property, shifting 1 and shifting 2 property. Then after that we have learned about scaling property. After that we have learned some theorems which are based on Laplace transform. Today, as we know that we have started our new chapter, that is inverse Laplace transform. Inverse Laplace transform. In this chapter we have studied about the definition of inverse Laplace transform. Now today we will go to find the theorems which are based on Laplace transform, in which first of all we have to study the linearity property. We have learned linearity property for Laplace transform. Today we will start linearity property for inverse Laplace transform. Correct? So we are going to see linearity property. We have going to see the linearity property, in which the statement is as follows. Let theorem is as follows. Theorem. Let f1 of s and f2 of s be from Laplace transform of Laplace transform of f1 of t and f2 of t, then prove that Laplace inverse Laplace transform of c1 f1 of s plus c2 f2 of s is equals to c1 f1 of t plus c2 f2 of. Correct? We have two different functions, f1 of t, f2 of t, and we have the Laplace transform of f1 of t as f1 of s, and Laplace transform of f2 of t is equals to f2 of s, where s is parameter with the Laplace transform of f1 of t and f2 of t. Then prove that we have to prove inverse Laplace transform of c1 f1 of s plus c2 f2 of s is equals to c1 f1 of t plus c2 f2 of t. Since where c1 and c2 are constant, where c1 and c2 are constant. Correct? We have one. Now, first of all, by using Laplace transform, we will since by the definition of Laplace transform, that is Laplace transform of f1 of t is equals to integration from 0 to infinity e raised to minus st f of t dt for f1. Similarly for f2, the Laplace it is equals to f1 of s, correct? Similarly, if we see Laplace transform of f2 of t is equals to integration from 0 to infinity e raised to minus st f2 of t dt, which is equals to f2 of s. And if we apply inverse Laplace transform on both sides, we will get inverse Laplace transform of f1 of s is equals to f1 of t, correct? And inverse Laplace transform to f2 of s will give us f2 of t, and it is our required inverse Laplace transform of f1 of s and f2 of s. Since we know linearity property for Laplace transform that is Laplace transform of c1 f1 of t plus c2 f2 of t is equal to c1 Laplace transform of f1 of t plus c2 Laplace transform of f2 of t. We have already seen this in previous lecture, or we can say previous chapter. So we have Laplace transform of linearity property for Laplace transform is equals to Laplace transform of c1 f1 of t plus c2 f2 of t, and is equals to c1 Laplace transform of f1 of t plus c2 f2 of t. And since we know that Laplace transform of f1 of t, we have Laplace transform of f1 of t is equals to f1 of s, and for f2 of t we have f2 of t. So we can write it as c1 f1 of s plus c2 f2 of s. Laplace transform of c1 f1 of t plus c2 f2 of t is equals to c1 f1 of s plus c2 f2 of s. Now applying inverse Laplace transform, we will get c1 f1 of t plus c2 f2 of t is equals to inverse Laplace transform of c1 f1 of s plus c2 f2 of s. And as you know that linearity property or inverse Laplace transform operator satisfied or distribute or addition, so we can write it as inverse Laplace transform of c1 f1 of s plus inverse Laplace transform of c2 f2 of s. Correct? So we can write it as inverse Laplace transform of f1 of s plus c2 inverse Laplace transform of f2 of s. Correct? So by using this definition, we can say that we have proof Hence proof, we have the inverse Laplace transform of C1 F1 of S plus C2 F2 of S is equals to C1 F1 of T plus C2 F2 of T. And it is the required result for our theorem. What it indicates? It indicates that the Laplace transform operator, or we can say that inverse Laplace transform operator is worked as similar as Laplace transform operator works. So we have seen in previous lecture the linearity property for Laplace transform hold good. Similarly, the inverse Laplace transforms also satisfies the linearity property, and whenever we have two different functions in addition, we can apply inverse Laplace transform and distribute inverse Laplace transform operator to both functions. So we can get easily this C1 F1 of T plus C2 F2 of T is equals to inverse Laplace transform of C1 F1 of S plus C2 F2 of S. And why we are learning inverse Laplace transform? Since in previous lecture we have already told you that whenever we come across a differential equation which is quite complicated to solve, we apply Laplace transform operator to convert that differential equation into algebraic form, and we have many methods to solve algebraic equation easily. So we apply Laplace transform to convert differential equation into algebraic equation, and after converting into algebraic equation, we solve that algebraic equation. After solution, we get a particular result in algebraic form. By applying inverse Laplace transform, we convert that algebraic solution into differential solution, and that will be easy to get result of that differential equation by using Laplace and inverse Laplace transform. In next lecture, we will see some more theorem based on inverse Laplace transform. Till then, thank you. Bye.